आइए हम सुने विज्ञान की अनकही कहानियाँ। आइए हम सुने विज्ञान की अनसुनी कहानियाँ। एक नई दुनिया की आवाज़ आपकी आवाज़, विज्ञान की आवाज़, की आवाज़।
Celebrating Azadi Ka Amrit Mahotsav, we bring you a podcast series on STEM popularization, science, technology, engineering, mathematics and medicine, supported and catalyzed by the National Council for Science and Technology Communication, Government of India. This program is produced by Media for Community Foundation. Creative content and technical support is given by Purvasha Banerjee and Shushanto Das.
एक नई दुनिया की आवाज़ आपकी आवाज़, विज्ञान की आवाज़, की आवाज़, की आवाज़।
We are extremely honored to have Dr. Saikat Biswas with us. He will also be introducing himself and focus on his academic journey.
Hello, I am Saikat Biswas. I am an experimental high energy physicist working at Bose Institute as an associate professor. I did my PhD from VCC Kolkata and I got the degree from University of Calcutta. After that, I joined GSI Germany, Darmstadt, where I was for 2 years as postdoctoral fellow. Then I came back to India with the DST ACRB Ramanujan Fellowship at VCC, and then I joined NISER as scientific officer. After that, in 2015, I joined Bose Institute as faculty.
Dr. Biswas will now briefly share his research work.
I am basically working on the physics of particle detectors, and I am currently involved in two international projects, experiments. One is called ALICE, a large ion collider experiment at CERN, and another is an upcoming experiment which is compressed baryonic matter at FAIR, Germany. These are two experimental high energy physics, and I am also working for the study of cosmic ray, but now I will be talking about FAIR facility and also the work what we are doing for the CBM experiment.
Dr. Biswas will now explain his research work in details.
Our group from Bose Institute, as I told, mainly involved in two experiments. One is ALICE experiment and another is CBM experiment. Both are high energy physics experiments, and in high energy physics experiments there are several steps, like you need to know what actually you are going to do. For that you need some preparation to set up an experiment. Maybe it is tabletop experiment, maybe it is a large experiment. For that you need some planning, you need to do some study. Those preliminary study can involve physics, can involve other aspect, for example like detector, where I am actually work on. Those work is called simulation. So that is done before the experiment mostly. Then you need to build the detectors and also the experimental setup. You need to plan, you need to set up that in the site of the experiment, and then finally once the experiment is over, then you need to analyze those data you have collected, and then you will get new physics. So there are three parts. We are working from Bose Institute in a group where we are three faculties. I am working there as well as Professor Supriyo Das and Dr. Siddharth Kumar Prasad. So we are three experimentalists who are working in this high energy physics experimental part. And our jobs are also divided. For example, I am working on the detector aspect of these experiments, and other two members, they are working mainly on simulation and on the data analysis. So, as I told, I am going to talk about the CBM experiment. Now, CBM stands for compressed baryonic matter. What is its main goal? So, I need to talk from little back. We know about the phase transition, like water to vapor, ice to water, such kind of phase transition we know what is very common. We want to study another kind of phase transition, which is basically from hadronic phase. What is hadron? The matter are consist of proton, neutron and electron. Now, among these three, these protons and neutrons, they are basically hadron who participate in the strong interaction, because in the universe there are mainly four interaction. One is called gravitational interaction, which is very weak, we all know. It is acting between our sun, earth, etc. Then another is electromagnetic interaction, what is very common to all of us. We can see light, etc. All are electromagnetic interaction. And then other two are strong interaction and weak interaction. Now, as I told, these hadrons, proton, neutrons, they participate in strong interaction only. And the other component, electron, they are lepton, another branch of particles, another group of particles, and they participate in electromagnetic as they have charge and also weak interaction. Now, this hadron, what is common, like we know the proton, but they are not the fundamental item. What is the fundamental constituent of matter? Who cannot be broken. But protons, for the time being, we all know that protons are not the fundamental, as they also have some more constituents. What are those particles? They are quarks. So, a proton consists of 3 quarks. Similarly, a neutron also consists of 3 quarks. Now, we want to see a phase transition between this particle phase, between this hadron phase to another phase, which is called the quark-gluon plasma, QGP phase. So, this phase transition can occur in two ways. One, we can take some particle and we can collide them at very high energy. Then those particles will be broken and they will make another phase, another shoot, and that phase is called the QGP phase, quark-gluon plasma phase. Another way we can also this transition. How? We will not increase the energy to a large extent, but we will increase the density of these particles. So, we will collimate those particles to a narrow part, narrow position, narrow area, and then we will see how they are changing their phase to the new QGP phase. So, this phase transition can occur in two ways. In CERN experiments, we basically do at low density but at high energy this kind of phase transition. But in FAIR facility, which is upcoming facility, there we want to see this physics of this phase transition, where the density will be very high, but the energy is not so high. This kind of environment we get at neutron star. So, such environment will be created at FAIR. That is why sometimes I also talk about that FAIR is the universe in the laboratory. So, we will create the universe in the laboratory. So, that will be done at FAIR. Now, to study this in FAIR facility, there is one dedicated experiment called CBM experiment, compressed baryonic matter, where a beam of heavy nucleus, you can take the example of gold. So, gold will come and hit a thin foil of gold. So, that thin foil of gold we usually call a target, and the beam is the projectile. So, gold will collide on gold, and then we will see what is produced. So, to do this, there will be an experimental setup, whole setup, and I am happy to say that one dedicated detector called the muon chamber, which will be built only in India. So, India will build and deliver the March system to CBM experiment at fair. In India, there are several institutes who are working for that, but mostly these detectors will be built at Bose Institute Kolkata and VCC Kolkata, because we have such facility to build such detectors. And I am basically working, and my group, my students, postdocs, they are basically working to build this facility. Recently, I will not tell recently, because one of my students already completed his PhD and he is now postdoc in UMass, USA. We are studying the performance of a particular detector which will be used in March system, that is called gas electron multiplier, or commonly known as GEM. These GEMs are very simple. You know, there is a plastic, of very thin plastic, 50 micron thick. So, you can imagine, and on top and bottom of this plastic there will be copper, and if you make or drill this copper cladded plate from top to bottom, then you will make a plate, and that plate is basically known as gem plate or gem foil. Now, on top and bottom there are copper, and in the middle there is some insulator, and now if I apply voltage, say 400 volt, then in these holes, as I told, I drilled holes, and this hole diameter is 70 micron, and the distance between center to center of two holes are 140 micron. Now, you can imagine in a small gem foil how many holes we can make. Before, this kind of foils were produced only at CERN. Professor Fabio Shauli, who was the inventor of this gem, and those gem foils were only produced at CERN. But now in India also there are industries, ECIL Hyderabad and also Micropack Bangalore, they are also producing this gem foil. But we are at Bose Institute, we are not producing gem foil, but we are getting the gem foil from industry and making the detector. So, we are just assembling 3 such gem foils on top of each other with a spacing of 2 millimeter, and on top of all these 3 there is another electrode which is called drift electrode, and then finally from the bottom we put one pad which is called readout pad. Now, if one particle come from top, they will ionize the gas which is there inside this chamber. So, this whole thing, these gem foils and these other electrodes, as I told, are closed in a chamber. So, this is a sealed chamber where special kind of gas we use, because these are gas field detector. So, we basically use very common gas, argon CO2, which is very normal and not poisonous, nothing. And then when this charge particle comes, ionization takes place, and then because of this high electric field, as I told, I will apply 400 volt across this 50 micron, and then 80 kilovolt per centimeter electric field will be generated. And then when these electrons produced on the top will try to go through these holes, there will be a multiplication. That is why the name is gas electron multiplier. And then finally, after all these 3 foils, we will get lot of electrons and they will be collected at the bottom, and then we will get a signal. So, presently we are doing the study of the stability of these gem chambers. We are doing this for quite some time, more than 5-6 years we are doing this. Several performance study we are doing in our laboratory, but very recently what we did, we found, as I told, between this copper cladding there is a kapton which is a high insulator. Now, when I apply very high electric field and large number of electrons try to pass through these, now if I told ionization on top when one particle is coming, now if the particle rate is very high, because gems are basically used where the interaction rate is very high, because I told in CBM the density of particle will be high. Now, you can correlate why we are doing this study. Now, when the radiation is very high, the number of electrons will be very high, and because of this, there will be in the kapton, there are an effect called the charging up effect, which is a lensing kind of effect, and because of this effect, what we get, we see that gain of this chamber is non a static one. It changes with time. When I start the chamber, the gain is low, and then slowly the gain is increasing with time, and this timing is called the charging up time. So, we have identified the charging up time for different kind of gem in our laboratory and found how this time is changing with the radiation rate. So, those studies are recently cited in our DST publications and newsletter, and those studies are very important for experiment like not only CBM, but also in other heavy ion or high energy physics experiment where the particle rate will be very high. This is one thing. This is the application in high energy physics I told. Another thing which is very interesting, the position resolution means you can identify 2 points who are very closely spaced, and still you can say they are 2 particles. Then you can say the position resolution of the detector is very high, very good. GEM has very good position resolution. So, GEM is very suitable for medical imaging. Nowadays, you know, we are doing the scanning with different kind of detectors. There also we use different detectors. So, GEM is also a competitor in this field as well. So, we can also use in future GEM for imaging purpose. So, I am also working on that, whether we can use GEM for normal use or not for medical imaging or any kind of imaging. That is also one of the field of study what we are also pursuing.
We are really thankful to Dr. Saikat Biswas for sharing his valuable insights on his experiments.